physics of laws. Let's get started. Tonight's getting away from us. When the pizzas arrive, we'll get them picking, so we'll make sure you can kind of get into the pizza. Alright, so tonight is special for you non-physicists because you get an insight into the brain of the physicist. You know, they're a strange species. And the next one, Andre Carvalho, is a particularly good example of a physicist because he had eye damage. Anyone else would go, oh my God, I've got eye damage, oh no, it's the worst thing ever. He goes, cool, physics experiment. So he can tell you all about it, all the way up from Griffith University. Please give a big hand for Andre Carvalho.
So what I'm going to talk about is basically what Phil just said. A little bit of how our brain works in terms of, we think, I mean, that's what I am. What am I? Theoretical physicist, right? In theoretical physics, we take our work home every time. And that's what happened to me basically a year ago. So that's the story of how I gained superpower and how I lost it. Okay? So it started here. So this photo is real, was the only photo that I had from my office. So that was back at ANU last year, was still at ANU before I moved to Griffith. And I had this little friend visiting one evening. It wasn't the same evening that the thing happened, but suddenly I was working in my office and this happened to my vision. Bang. Right? First thing that comes to your mind, there's something wrong with my brain. There's some problem there. And then you start to move your eyes around, and this thing's still there. And you say, I have some problem in my eye. You try to do the emergency, and then go to the hospital. And people say, oh yeah, you have a problem, but you don't think it's something very serious. Come back tomorrow. Okay? So that's what happened. And then the next day, congratulations, you have retinal detachment. So, what is that? So let's go to our eye here, so that you have an idea of what's going on. So that's our eye. So this gray area here is the vitreous material, so the kind of fluid that we have inside our eyes. And then we have the retina, that's the back part here, and then we have the back of your eye. So that with age, as you can see from my hair, right? So this vitreous material starts to kind of form some blobs of fluids, and it starts to detach from the retina. That's what the first doctor thought that I had, was kind of this vitreous detachment from the retina, which is not so bad. The point is that as you move your eyes around, and this thing is detached, as if you move, for example, my glass of water around, the water is kind of trying to go together with the wall of the glass, right? But because I have this small detachment here, what happens is that sometimes that fluid wants to move around, and as it moves around what it does, it pulls away from the retina. And sometimes it does it so strongly that, bang, you make a hole, a tear in your retina. Not good, right? It's like having a crack on your wall. What happens when you have a crack on your wall? Sometimes just you have humidity, infiltration, then with time, just pulls off, right? That's what happened with me. So I had this tear here, the fluid was getting behind the retina and was pulling it out. So what I was seeing here was basically the shadow of this fluid getting behind, all right? So then I was talking to the doctor and I was listening to the doctor talking. And I was looking at the doctor just making his sketches. And then that would be the sketch of the left eye. He was drawing this thing in there. And I was looking at that, he was pointing out the tear in your eye and then pointing up. And I said, come on, I'm seeing this. He's pointing up there. And then I remember basic high school physics, lenses, right? When you think about if you have Okay, that's my attempt to draw awesome. You have your object, and then that's your eye, and then you have a lens. That's the lens of your eyes. When you just draw the rays, of the light getting to retina, we know that the image formed in your retina is inverted, right? But our brain gets that image that's inverted, and whatever complicated process that we have behind that we transform that into something that our brain understands, right? It somehow inverts that to something that's upright. So what was happening was that the image of that shadow in my eye was in the upper right corner. Therefore, my brain was positioning that way in the lower left. So, first physics lesson of this. Yeah? And then it was kind of, if this were a movie, it would be that moment where the voice of the doctor would start to fade away. and all the kind of my inner voice about the physics started to sorry, moving the microphone away. My inner voice said, oh, cool. Right, so yeah, exactly that. So I'm a theoretical physicist, I don't happen to do experiments, but that was cool. I was the experiment, right? So that was happening there. So, but then at some point I had to kind of pay attention and that's also something that you can actually buy. So those glasses here, they are glasses that they invert the image. So they have prisms there, and people have done experiments with that in neuroscience and psychology. You just use that, everything turns upside down. Literally, you can Google, see on YouTube, and then people trying to pour earcon teas, seeing everything upside down. It's crazy. But after a week, for example, your brain just adapts, and then you can function normally. Anyway, then the thing kind of got me back to reality was when the doctor started saying, okay, 4 minutes. Okay, we have to do surgery. What are the complications? Okay, you are probably going to develop cataract, right? Everyone will at some point in their life. You can get infection, complications from surgery, loss of vision, then you start to get scared. And then I asked, okay, what if I don't do the surgery? I said, okay, if you don't do the surgery, you're going to have a full detachment. Probably your retina, after it gets fully detached, it's going to, of course, you're going to lose your vision. And on top of that, there's going to be less vascularization, so less blood coming to that. Your eyeball is going to shrivel, and then fall from your eye socket. I looked at the doctor and said, so you mean that, okay, my option then is, I either do this surgery, okay, that's the worst image I'm going to show, I promise. Or, I'm becoming a living character from So that was one of my options. So, okay, surgery it is, same day, we do the surgery. How this is done? So, okay, I was completely knocked out, great, didn't see anything. So they come into your eye, they remove parts of the vitreous material, they suck the water, they bring it out, they come with lasers, they just bang the lasers there. Sorry, just bang the lasers there, and then it's like, so the scar of the laser is basically like a glue. So it's fixed there. If you were fixing the crack on your wall, you're just going to put some plaster. The difference here is that you have to hold, imagine that when you glue something, you have to put some pressure to hold that, right? So the doctor can't really put something there holding the thing. So what he does is that he pumps gas inside your eyeball. So your eyeball gets gas just to hold the thing in place. Pretty cool, right? Yeah. But it's really cool that you get this bracelet saying, okay, this guy has gas in the eyes, don't let him go into airplanes, or I couldn't even kind of drive from Canberra to the coast because that's too much of a difference of pressure and so on. Now, that second lesson of physics could have been worse. Why? Because the gas has to stay there fixing your tail, right? So if my tail was in the back of the eye, we know, so gas is less dense than water, then the fluid would go out. So if my tail was in the back, would be like this. So that's my iris, so this is the liquid, this is the gas would be there. So that's the poor guy having to sleep for 10 days in this position so that the gas is in the right position. In my case, I just had to sleep sitting down because my tail was kind of up. So I couldn't just, it was the week of the Olympic Games, so I was just watching that. Not a problem. Alright, so now the really cool thing happened the next morning. So they took my eye patch and then get the doctor to take the pressure of my eye. I don't know if you have ever done this. Nowadays, if you go to the optometrist, you just lay in there, they just come with puffs thing in your eye, right? So that's what this does, puffs something in your eye. So it came to my right eye, and then there's a pointy thing coming, and then you don't see anything, right? No one can focus here. Now it came to my left eye, and then the thing was getting bigger, and the thing was huge. So basically I discovered that I had my superpower. I could focus. I had basically a microscope in my eye. So with all the gas inside, completely changed the index of refraction of my eye, and the thing could just magnify things greatly. The point is that to have the magnification, the thing had to be here. Literally kind of touching my eyelashes. Right? So, and then I said, okay, that's Facebook history term. All people then said, yeah, I have my own super magnifying glasses. I mean, really super. That's what I have. Alright, so of course this is not what I was seeing, but I did some calculations. And this I took from my iPad when I was sitting down at home. So that's the physicist at work, right? And I said, yeah, okay, magnification, that's my thumb. Okay, with my right eye, I more or less, okay, I used to be able to see at 25 centimeters, now it's getting further away as age comes, right? And that would say more or less the size, and then I said, okay, if I'm really approaching here, because this was focusing really at around half centimeter, I'm getting a magnification of about 50, give or take, right? 50, is that real? So I went to the internet to see some pictures, and that's 50, 200, 200, 500, and I wasn't too far from that. If I would look here, that's what I would have to do. Right? That's more or less, maybe it was a little bit less, but wasn't too far. So my little back of the envelope calculation wasn't too far from that. So that was good. Alright, now another thing that I did, sorry about the microphone again. So another thing that I did is that I learned to manipulate images just to make my friends see what I was seeing. So what I had here is my right eye. I was looking through the window of my house, and this was my left eye, day one. I couldn't see a thing, right? Of course, my eye was full of gas. I had no idea what, my eye wasn't able to focus. Some days later, I saw this. And you see this kind of area here. So this top part is more visible, and the lower part is not visible. So this lower part is what? Gas. Why?
Because it's rising to the top.
Exactly. The gas is to the top. You know that our image is just reversed. So this part here is the liquid, and this is the gas. So I could see the gas kind of coming down with time and reducing. And this is more than a week later. The central part here is the gas. If I would look down, the gas would go to the back of my eye, and I would see that. It would work as a magnifying glass. So I spent 10 days really experimenting with that and having fun. Literally, yeah. So unfortunately, the super magnifying thing only lasted two to 3 days, and then started to go away. So in the end, what happens is that I indeed developed cataract, as the doctor predicted. So this was me yesterday. I had cataract surgery yesterday. So they put something like that in my left eye. So my left eye now can see you guys thanks to this plastic lens, which means that that's the first step towards my cyborg life. I'm looking forward for plastic knees, feet, and all that. That's all I have to say. Thanks.
Wow, that was great. I'm going to try and attach more on this tonight, so I'm going to say that. Look, one of the things I've learned since moving from doing a PhD in laser physics to becoming a science communicator, and starting to study how people communicate and what things, really connect with people and stuff. And I started thinking about the great storytellers in our culture. Literature and religion, they make stuff up. It's not always right. You know, there are all these parables about Jesus did this, or somebody. There was a particular story when I was a kid that connected with me at Sunday school about this guy who dies and he's looking back at his life as a series of footprints on the beach. Now that didn't actually happen. This is a story to illustrate a point. And it made me think, I've been thinking more and more about physicists needing to be able to tell stories and not bother about this truth and fact and all of this stuff. And Trump has really taken that, you know. So I'm going to teach you guys a bit of physics, okay? But it's going to be through the vehicle of something that didn't happen, that is complete bullshit, that is completely made up. But I really hope that you will learn something from it and maybe even remember it. So here we go. Doesn't all love a fairy tale. Once upon a time there was a handsome prince who lived in a beautiful yellow castle. He loved the colours of the world. He loved the green of the grass. He loved the yellow of the sun and the blue of the skies and the reds of sunsets. He was a bit of an amateur physicist, so he really liked rainbows because not only are they beautiful, but they demonstrate an amazing thing, which is that the sun's light is actually made up of a whole lot of different colours, and when you split them out using a water droplet into a prism, then you get the rainbow. So there was only one thing lacking in this prince's life, of course. He was lonely. So he decided he would search for a partner who could colour his life even more brightly. So he put it on the Palace website, he put it on Snapchat. He was thinking about using LinkedIn, but he didn't really know what LinkedIn was for. Does anyone? And suitors came from across the land. The first was Lorraine, and Lorraine said, "Prince, I am an astronaut, and I'm fascinated by why the sun is yellow." See, it's yellow because of a phenomenon called black body radiation. When something at room temperature that's black, you heat it up, it begins to glow red, then it begins to glow orange. By the time it's at 5,000 degrees, which is the temperature of the sun, it's glowing yellow. That's why the sun is yellow. So what I propose to do, Prince, is to, using my superpowered rocket, drag the Earth into orbit around a completely different star. This one, a blue giant, because every fairy tale needs a giant. And this isn't a yellow star, this is a UV star, 4,000 degrees Celsius. It's a type O0 for the star nerds out there. Star nerds. And so this is what your world will look like. See, it peaks in the UV, so it gives a lot more of the blues and the greens, but less in the oranges and the reds. So the world will become more blue, the sun will be blue, the sky will be the sunsets will be kind of green. And the prince said, "Look, I'm not sure that's going to actually enhance my rainbow. It's probably going to make it, a little bit worse, there'll be more blues, but less comparatively of the oranges and the reds. And all this ultraviolet is going to damage our eyes, which we've just learned actually could be cool. And it will give us skin cancer. And there's one other thing that bugs me about this. You see, the Earth is in the Goldilocks zone, the astronomers call it, where it's just at the right temperature where it doesn't freeze, where it doesn't boil. So with this super hot star, we'll need to be further out, we'll need to have a much bigger orbit, and the year will be longer. And Lorraine said, "Yeah, that means that winter will come around less often." And he said, "But summer will come around less often too, duh." And she said, "Yeah, but my birthday will come around less often, and I'll stay younger." And he would, "You were the kind of princess I'm not interested in." The next suitor was Jane, an astronomer, and she said, "Prince, I'm fascinated by why the sky is blue. That's a process called Rayleigh scattering." So Rayleigh scattering is whereas the light from the sun bumps into the nitrogens and the oxygens in the atmosphere, and it tends to bounce that light around, and it bounces the blue part of the light much more. So in this end, you see nearly a quarter of the light gets scattered, but the red end, a lot of it just keeps going. And that's what we see in our world. The sky is blue because the light passing over us, the blue bit gets scattered down to us. When it's sunset, then the blue has been scattered away and only the red has made it through with this very long, low angle through the atmosphere. So, friends, I have sent a rover to Mars, and the sunset on Mars is like this. You can actually see from the red dust in the atmosphere that the red part gets scattered, the opposite of Earth. So you get a red sky and you get a blue sunset. How about that? My proposal for you guys is to pump hundreds of billions of tons of red dust into the atmosphere, and this is what the Earth will look like. You've got a red sky and a blue. Prince says, really? Because we still have the atmosphere, right? Or you're proposing to get rid of the oxygen, and as soon as there's that'll be working against you, right? You'll still have the radius gathering in, so we'll just make this sort of messy brown colour. And as soon as there's a big rainstorm, all the red dust will just come down and coat everything in. And Jane said, yeah, right, my theories only work for a spherical planet in a vacuum. Physics joke. The third suitor was Elaine, and Elaine said, Prince, I'm fascinated by why the grass is green. She's a bit of a botanist, a bit of physics. She does genetic modification. I do multidisciplinary science, she said. And the Prince said, oh, that's sexy right now. So, I'm fascinated by the way grass is green. You see, it's because of chlorophyll. And chlorophyll, which is in the plants, absorbs the red part of the spectrum and the blue part, but doesn't use the middle. It bounces back the greens and the yellows from the middle of the spectrum, which is kind of silly, given that that's the middle of the sun spectrum, that's where the most amount of energy is. So I propose to genetically modify grass to use that middle part and not bother with the reds and the blues. So what happens when you put red and blue together? You get purple. And the Prince said, my God, purple grass, my favourite colour. And there's one more thing. That is going to capture more carbon because chlorophyll is more efficient. So you're going to reverse global warming. You are my hero. Will you marry me? And they lived happily ever after. So at the wedding, he sang this song that I want you to join in. I can see clearly now the rain has gone. All the red dust has washed away. Gone is the blue time that had been gone. It's only a while. The sun is so far away, scattered. The sun is so yellow, cause it's not too hot. And it's my birthday every single year, and Christmas too. We'll be a ride. You go around, there's no man with sunlight. You straight ahead, there's no sunset. I think I can make it now, baby, it's good. All the cool been praying for. It's gonna be a bright, 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 bright colored day. It's gonna be a bright, 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 bright colored day. Gonna be a bright, bright, bright standing ovation. Goodness me. Why don't they be someone? All right. Let me just overcome my quick hot flash here. What's happening next? I think we've got another bit more music here. So, look, I live in Canberra. Chris lives in Brisbane. So we haven't practiced. But let's have a go anyway. Come on, welcome to the stage, Chris Masiku.
Hey everyone. How are you going? I think some of the UQ physics people have probably seen me around. For everybody else who hasn't, I was a physics graduate. I worked in astronomy for some time until one day I made an extraordinary discovery. I discovered I'm actually human. Any other physicists have done that yet? The point is this, right? The way we do physics sort of eliminates that. We sort of don't acknowledge that we are human, as it were. I'll explain to you what I mean. Today, right, we have heard all these different stories. We've heard fusion, we've heard supernovas, and many other things. And all the things that, gather all those together is this thing, human emotion, imagination, creativity, and so forth. All right? So this is really important. It's National Science Week, and what's the theme? Ignite your imagination. Human! Yeah? So it's really important, and it's the reason why I'm doing the PhD that I'm doing now. So I left the astronomy and went to really look at, well, how do we, especially in physics, acknowledge our humanity and still not sacrifice physics? You know, it's a pretty big deal to me. All right. So as I say, fusion research is emotional with imagination. Supernova research is emotional and fused with imagination and values. Pluto is emotional, full of imagination. Losing our jobs to AI is emotional, full of imagination. Eye damage is emotional, and it makes physicists want to calculate magnification. Imagination matters to physics, but imagination is tied to values, and values is for humanities and not physics. Physics is fact. So what is actually happening is we are led to do physics by denying ourselves. Something's wrong there, and I want to get to the bottom of that. And just to tie in with this, when I was studying my physics undergraduate, I watched Young Einstein. Who has watched that movie before? Now that is a movie I like because it precisely combines all these things, right? The importance of the imagination and all these different parts. So I decided then when I was first year undergrad, I'll make my own Einstein song, and that's what I'm going to perform today. A reggae tune, and the crowd is supposed to join in so you can all appreciate the fact that you're human, even though you're doing physics. All right. So there's a part where the crowd gets involved. It's the chorus. So in every chorus, I'll say, Albert Man said, I wanna be a genius, and you people will shout, you know that man. Beautiful. Let's practice that. And Albert Man said, I'm gonna be a genius. Come on. Embrace your humanity. Not the formulas. Okay, once again. And a little bit man said, I'm going to be a genius. You know that man. So, let's see where. I hope I've got it. After all this, and I'm glad there's physicists here because you'll hopefully understand the song. Okay, here we go. So, Albert Einstein was born in 1879 to his lovely mama, Pauline Einstein. Happy she was, cause he was a good boy, so she gave him a toy. But Albert man said, I'd rather be a genius. You know that man. Yeah, I'm gonna be a genius. You know that man. When a very small boy at the age of 5, his papa Hammer gave a pocket compass. He turned it up, ha ha ha. Now you can become a pilot. Albert man said, no, I'd rather be a genius. Yeah, I'm gonna be a genius. But his life was high as he looked for a job. Lucky he found one at the Institute of Zurich. But I'd rather be a genius. Yeah, I'm gonna be a genius. At the age of 23, he stated E equals to MC squared. E equals to MC squared, or energy equals to the mass times the velocity of light. Energy equals to the mass times the velocity of light. Yeah, but Albert man said, I'd rather be a genius. You know that man. Yeah, I'm gonna be a genius. You know that man. And relativity was an easy one in 1921 when Albert man said, stand to the metal, electrons escape metal because light was a particle. And not away, then the Nobel cried yes, and Albert man said, I have a Nobel Prize, you know that man. Yeah, now I'm a genius, you know that man. Yeah.
Sensational work, thank you, Chris. Just amazing. Okay, so we are approaching the climax of the show. So we have the fabulous Mr. Aidan Suter here, who is really interested in fake news, alternative facts, and quantum physics. So big round for Aidan Suter.
Hi everyone, I'm Aiden, and I'm going to be talking to you about one of my favourite subjects, which is fake physics. Oh, wait, this isn't the starting slide. Quick, go to the beginning, please. That's a spoiler. That's also a spoiler. Okay, so yeah, I'm talking about fake physics, and I think every physics student goes through a stage where they love looking up these crackpot theories. So first of all, I'd love to specify what is fake physics. So to me, that's two types. First, we have the fictional type of physics, time travel and sci-fi. We have cartoon physics where a beam lands on a fuel tank and it explodes, that kind of thing. I think that's mostly harmless and pretty good. The second type is the pseudoscience and alternative physics. So we have crowdfunding scams, science denial, and the University of YouTube where you find out the flat earth theory. So I feel it's important we define what I mean by pseudoscience more rigorously. So I found this list online, which is apparently from a psychology journal, and they make a few points. So one sign that something is pseudoscience is that it involves a lot of jargon and technobabble. Another is reliance on anecdotal evidence. But most importantly, the point I want to point out is that extraordinary claims are given in absence of extraordinary evidence. So the rest of these points really just come down to a lack of evidence. So the first example of fake physics I want to give is there's a guy online and his name's I think Scott S. Gordon or something, and he claims he's found the theory of everything. And there's a couple of clues that he may not have actually found the theory of everything. So the first of these is that his equation is trademarked. And every time he posts this online, that trademark symbol is there. And that's a bit baffling given I don't think this is his original equation. Moreover, I think he misunderstood that the E in E equals MC squared doesn't stand for Einstein because he has put his own name in there, G for Gordon, 3 times, just to solidify who it is. But if we look at him actually talking about his theory, what you'll notice, this is a comment from Quora, he refers to himself in the third person and constantly compliments himself, where he says, what Gordon did was to make 2 very intuitive postulates for his theory of everything, and then he goes on to talk about some stuff that doesn't really seem to say anything in particular. Anyway, so that was just an introductory theory, but I'd like to move on to my most favorite type of fake physics. And this is an area called vortex mathematics, and this is from a TEDx talk given, I think, in 2010, where Randy Powell and his supervisor, Marco Rota, this is Randy Powell here, claim that they've unlocked a mathematical mystery that's baffled scientists for millennia. And I'll just let this video tell you what they say vortex mathematics can lead to.
What we have is the grand unified field theory. With it, you can create inexhaustible free energy, end all diseases, produce unlimited food, travel in the universe, build the ultimate supercomputer, artificial intelligence, and obsolete all existing technology.
Okay, so if we remember back to our pseudoscience list, point 3 was extraordinary claims require extraordinary evidence. And I don't know about you, but I think those are extraordinary claims. I mean, cure all diseases, travel anywhere in the universe, that sounds pretty good. So let's see what evidence they have. So we go to his YouTube channel.
We have the grand unified
YouTube channel. There we go. So we go to his YouTube channel, and we look at the first lecture in a 4-hour lecture series explaining what vortex mathematics, the basis for his theory is. So remember, he claims that this has baffled mathematicians for millennia, and this is what vortex mathematics is.
Okay. So we start with 1. What is 1 doing on the symbol? Well, if we draw a straight line connecting it to the next number, it goes to 2. And what that is called doubling. 1 double becomes 2. 2, if it doubles, and we follow this line again, becomes 4. 4, if we double, then following our line, becomes 8. 8 doubled in is 16. How comes that? Because if you add 6 and 1 together,
so, I mean, I'm a bit skeptical at this point. All he's done is add numbers under 9 and then added the digits together. I think we need to give him a chance. You know, this was only 10 minutes into a 4-hour lecture series, so if we skip ahead several hours... 1, 2, 4, 8, 7... And I'll save you the hassle of watching 4 hours of vortex maths on YouTube. And I'll tell you, for that 4 hours, he just adds numbers under 9 and then adds the digits together when he gets over 9. Yet somehow he ties this into concepts like space-time implosions and things like that. So at this stage, the theory behind vortex maths and this theory of everything is seeming a bit dodgy. But you know, maybe they've got experimental evidence to support their claims. And in fact, they show a demonstration in their TEDx talk of the Rodin coil, or as Randy likes to call it,
referred to it by Marco's name, which is the flux thruster atom pulsar electrical venturi space-time implosion field generator coil. Create a localized space-time implosion, controlled desktop black hole. That magnet is still spinning. There's no energy in the coil. This is the final technology, the philosopher's stone, the reactionless drive unaffected by any weight that it carries. It's a true model of an atom, and with it I have the key to the periodic table, which a professor from the University of North Carolina told me could be the greatest scientific discovery of all time.
So I do love how at the end there he says a professor at a university has told him this could be the greatest scientific discovery of all time, and he sounds somewhat annoyed as if, yes, I already knew that, I don't need some crank to tell me that. But what I also want to point out is the rotocoil, the flux atom thruster space-time implosion, whatever it was called, seems to just be a copper coil with, despite saying it's not powered, seems to have a battery next to it, so I'm a bit skeptical of that. Anyway, I think at this point you should agree with me that this is not real science. And you would think maybe the TEDx organizers would, apologize to the audience for, not vetting their speakers thoroughly. But in fact, if you go to the TEDx website to this day, the organizers state, above a list of speakers where his name still stands, it was an amazing day where every speaker really nailed it. Now, I'd like to point out that several professors at the university actually reached out to Randy and they asked, can we see some evidence and can we, see some data to support your claims? As you might expect, they never got back to them. Anyway, one scientist was saying, wow, such fucking bullshit. Now I don't have time to go over more fake science than just this, but I'll maybe go over some examples of real mathematicians and physicists having some fun. So I'll skip through this. So this is one of my favorite examples of mathematicians and physicists having fun. And this is where a website called MapGen, where you can randomly generate your own mathematical papers. And what it does, you put it and it creates you something that looks very professional and legitimate, but is absolute complete nonsense. And if you show it to your friend and you go, oh, I don't understand this result, you feel intimidated because it tells you it is well known that. In some cases, it will tell you every high school student knows this. And so the key to this is every individual phrase makes sense or seems legitimate, but when put together, it's utter nonsense. And one woman in America, I believe, she submitted one of these randomly generated papers to a predatory journal, and they accepted it. And this was their feedback. One of them said, for the abstract, I consider that the author can't introduce the main idea and work of this topic specifically. We can't catch the main thought from this abstract. And she replied, the referee's objection is well taken. Indeed, the abstract has not the slightest thing to do with the content of the paper. But apparently that's only a minor problem and isn't going to stand in the way of publication. We have another thing where the journal stated that the proofs weren't sufficient, and here are the proofs. It just states this is obvious and this is clear. But another very well-known incident of this was that one man was on the emailing list for a predatory journal. Say, "Oh, publish it fast, just pay the $500 fee," and that's a good opportunity. He kept telling them, "No, take me off your mailing list, take me off your mailing list," and they never did. So he decided to submit a paper, and that paper was entitled "Get Me Off Your Mailing List." We have a very nice abstract here outlining and then some highlights from the paper. And the best thing was they were happy to publish this paper if we paid them $500. And so the point I wanted to make with my talk here was that from the outside, it's actually kind of hard to distinguish real physics from fake physics because the terminology and all these things are so dense and hard to interpret that it's kind of hard to take something like this and say, is that real or not? Like I wouldn't be able to tell at a glance if this was real or not. And especially the problem is worsened when we have real physics and math papers with names like these: ham sandwich of mayo, a stronger conclusion to the classical ham sandwich theorem. 10 equals 6 plus 4, which is vortex maps as far as I'm concerned. And my favorite, not only is the title of this paper, Ferroelectrics Go Bananas, but the entire paper actually compares the ferroelectric properties of a real banana to something that's just nicknamed a banana. And they actually have a reason to do this. Anyway, I think I'm out of time, so thank you for listening.
finish off with there's something I've got to do. Because a lot of people come up to me and say, hey, you do science and music, so why don't you do that Tom Lehrer song? You know, there's hydrogen and helium, you know that song. And I'm like, come on, that's so 19th century. Okay, he did it in 1950, but the science is from the late 19th century when Labour was working out the periodic table. The song he uses is from the Gilbert and Sullivan operetta, the Pirates of Penzance. So I'm like, it's enough time to come forward a couple of centuries. Don't get me wrong, the periodic table is awesome. Okay? The way they took all of the mess of minerals around us and managed to work out order so that you can see that as you add element 1, 2, 3, 4, 5, 6, 7, they fall into these beautiful patterns where you have all of the gases over here, all of the metals over there. And what it showed us was that there was a structure in the atom. And it was to do with the number of electrons that were running in the outside. So there's hydrogen, one atom, helium. It's got a full shell. It's now not going to hold much. It's a gas. And the same then you go lithium, beryllium, boron, carbon, nitrogen, fluorine, neon. I've dropped someone along the way. Neon's a gas as well. It's got a full shell. And then you keep going, you do the same thing. You don't need to learn all those damn lyrics. Do you? You can just say, okay, this is all we've got. We've got an atom that's made up of an electron in the outside. In the center there's a nucleus that has protons and neutrons in it. And in each of those there are quarks. And quarks come in two flavors, two types. So this is our periodic table. Up, down, up quark and down quark. Two types of quarks and an electron. I mean, try making a song out of that, up, down, electron. Fortunately for us, it was a bit more complicated than that. As physicists developed the technology for studying high-energy particles coming out of radioactivity, for example, carbon-14 spits out an electron very fast and turns into nitrogen. And nitrogen recoils like it's fired a gun. But when you fire a gun, you recoil this way. The nitrogen was recoiling at funny angles, going this way, up that way, all over the place. There was a big puzzle there. And the answer was there was something else coming out, which was predicted around 1930 when this was first observed. But it took 34 years to actually observe a neutrino. Nowadays, we have neutrino detectors like this one. It's called Super Cameo Candy. It's in the bottom of the mine shaft in Japan. What other country would call it Super Cameo Candy? Okay, I'd like you to hold up your fingers like that. We now know that neutrinos are produced in nearly every solar fusion reaction. In the time that you held that circle up, 70 trillion neutrinos went through the circle. They're coming from the sun, which is going to the west and below the horizon. They're coming through the Earth, they're passing through there, they're passing out through the atmosphere, through Mars, Jupiter, Saturn, and off into space without hardly touching anything. There are trillions of these neutrinos all around us, but we've never seen them. Turns out, we also discovered that there's an opposite for everything that we see. So for example, for electrons, the negative electron, there's a positive electron, positron, and this is antimatter. Okay, so let's go back to our periodic table. We have 4 things in our periodic table, and we have another 4 which are the anti-partners of those. But we can kind of ignore them, they're just opposite spin, opposite quantum spin, and opposite charge. So we'll just forget them. Of course, it wasn't so simple. This is the technology they used in the middle of the 20th century to discover particles. It's basically like a mist, and as a particle goes through, it leaves behind a jet trail. As a jet flying overhead leaves a trail in the sky. You put a magnetic field around it, and it makes the tiny jets go in crazy spirals, so you can see what charge they are and so on. And physicists discovered there were just hundreds of particles appearing and disappearing. Just popping into existence and disappearing again. And it was kind of like the whole scene with Mendeleev again. There's all these things that we have no idea what they are. How can we sort them into some order? Here are just some of the particles that they found. These they categorised as mesons, and these ones are categorised as baryons. My particular favourite is this bottom one, the double charmed boson omega. Anyhow, it took them a long time, but they managed to work out what was going on and build the new periodic table. The first clue was a thing that behaved just like an electron, but was several hundred times heavier and lasted several milliseconds before it exploded in a puff of energy. Then they discovered there had to be a corresponding set of quarks and a corresponding neutrino. Next, they found an even heavier electron called a tau electron. And that had a pair of quarks which they named top and bottom, and there was a neutrino as well. So here we go, we've now pretty much got our new periodic table. The top ones are called hadrons. They always form into pairs or triplets. The bottom ones are called leptons, and they tend to hang out solo. What was amazing though, so here's a bit of a summary. You can see how protons and neutrons are made. There's two ups and a down, two downs and an ups, and so on. We'll come back to that later. What was interesting about this theory was that it also managed to explain some other weird phenomena. If you have a magnet, how does it know that a piece of metal is over here? How? It can do it through a vacuum. It's extraordinary. So this theory, quantum electrodynamics, Richard Feynman was one of the heroes of this theory, explained that what was actually going on was when there was a magnetic field, there was an electromagnetic thing travelling called a photon. Now that's what light is, that's the light coming from these lights. But it turns out photons also carry electric force. So this diagram shows two electrons coming together, bouncing off each other, and in the middle there's a bit of virtual photon flipping backwards and forwards very quickly that carries the force. And there's the similar thing for the other forces, with a strong force that holds quarks together, for the weak force that causes radioactivity. Here's an artist's impression of what gluons inside a proton, how they're not stationary, that's a snapshot, they'll be flipping backwards and forwards and holding the whole thing together. So, our periodic table gets even better. There are four forces. The electromagnetism is carried by a photon. Strong force is carried by a gluon, that glues things together. The W and Z boson carry the weak force. Boson means that you can have a hell of a lot of these particles. You put electrons in a bucket, eventually the bucket fills up. But if you put photons, if you shine a light into a bucket, the bucket never gets full of light. You can have as many photons as you like, and that's the definition of basically of a boson. You can have lots and lots of them all together. So, some of you will have noticed there's something missing. The most famous of all of these bosons, and it's all down to this guy on the left, Peter Higgs, getting his Nobel Prize after predicting the Higgs boson back in the 60s, and was finally discovered in 2012. So that day was the last thing, the 17th particle, and it doesn't explain gravity. This is all quantum and electrodynamics, and quantum gravity we don't understand. It's really something we don't get. So we now have the Higgs boson, which at least tells us a little bit about why these things have such strange masses. But anyhow, this is the new periodic table, called the Standard Model. And so to finish the night off, I'd like you to join with me in apologising to Nirvana for the next song. And sing, please. Explain forces behind us, like hydrogen, helium, atom, proton, neutron, and organ. Hello, boson. Hello, proxy, heroes, drop the terror, Mr. Hero, standing on earth. It's much clearer on the commandments. Smash up atoms, matters on the quarks and leptons, like neutrinos, and neutrinos, and neutrinos, so many fucking neutrinos. I'm really humans, there's united the cracks in rain, and downs and ups, electrons swell, can't break them. Quark charge, 1/3 and sometimes 2. Electron, 3 quarks, these are 1 and 2. Electrons, electrons, neutrinos 2. But wait, there's 3 more growth. There's a quark, and a down 1. Strange charm quarks, top it up quarks. Down muons are electrons, and neutrinos. Coming 3 moons, down neutrino, new neutrino. And they flip around those freaking neutrinos. What? It's no sin to split the charge and a quantum spin. A photon's light, its waves of course, but carries the electromagnetic force. A photon's light, it's just a photon, could be quick. It's virtual, too fast to see. They find the quarks in the interactions. All photons, electromagnets, not just photons. They're destroying from one to the one. I'd say photon, neutrino, that one is not special. God's no photon, just use 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 photon. Thank you very much. Big round of applause for all our presenters, for the support from the launch, for the support from National Science Group, from the AIP, the Australian Institute of Physics,